Alright guys, today we're going to be solving yet another coding problem under the backtracking pattern, and I feel once you completely understand this problem you'll be able to solve similar combination related problems. And so let's dive right in. So let's just first go through the problem statement. Given a list of positive integers and a target, return all possible combinations of those integers that could sum up to the target. So the problem statement is pretty straightforward. We're given a list of positive integers and we're given a target number, and we need to find out all the combinations of these integers that could add up to the target number. So based on this example here, 2, 3, 6, 7 are the positive integers given to us, and obviously the combinations of these integers that could add up to 7 would be 2, 2, 3, 2 plus 2, 4, plus 3, 7, and 7 itself. And there are no other possible combinations that we can use to add up to the target 7. So now that it's pretty straightforward, now that we have understood the output, let's set it aside and try to understand our state space tree for this problem. Well, now for the state space tree, as we have already done before, the first thing that we'll try to understand is what each node is going to hold. So our state space tree will help us to solve this problem, right? So let's look at it from a top-down form. So top-down form would mean you have a target 7 and you have to kind of bring it down to 0 by using all of these integers. Now, how would you bring down your target number to 0? You would obviously try to subtract these integers from it, right? So every time in a state space tree, every node in your state space tree is going to determine the target value left, right? So initially the root node of your tree is going to have the target value 7, and as we try to subtract these numbers from 7, we will have further nodes that will hold smaller and smaller target values until we reach a target value of 0. Now, what is the exit condition, right? Exit condition is going to be when the target value is 0, right? It should not be less than 0, it should not be greater than 0, but it should be equal to 0. Now that we have identified what our node will hold and what each edge will hold, let's also add an edge. Now each edge, as I said, will hold the integer to subtract from the target, right? So the node and so all the edges that are connected to a node will determine the integer that we are trying to delete from that target value that the node is holding. So I've tried to kind of create this tree example using the input array given to us and the target. So we start at the root node, which is 7, and we have 4 options that we can delete from, that we can choose from to delete from 7. So we have 2, 3, 6, and 7, right? 2, 3, 6, 7 in the input array. So let's say we first subtract 2 from 7, we get 5. We subtract 3 from 7, we get 4. We subtract 6 from 7, we get 1. We subtract 7 from 7, thankfully we get 0. Now the 0 is, as we mentioned in our exit condition, when the target value is 0, that's when we have reached one of our solutions. So the path 7 is a valid solution, and that's why we have 7 in our output. Now let's see what other paths lead us to. So you subtracted 2, so you have used 2 ones. Now you can again start at 2 and you have 4 options again to delete from 5. You got 2, 3, 6, and 7. Now you can delete 2 from 5, you get 3. You can delete 3 from 5, 6 from 5, 7 from 5, and so on. So obviously we cannot go any further with the negative options, but we have 2 positive options right here. But as you can see, the first positive option is 3. You again have 4 options to delete from: 2, 3, 6, and 7. Now as you can notice here, when you delete 3 from this node, you get 0. And thankfully this is one of our other paths that we have reached. So as soon as you hit 0, we know that we have reached our solution. So the so the digits, integers that we have used so far in our path would be 2, 2, and finally 3 right here. And so that is our output. And so these are the only paths that lead to 0. You can try out other paths, but they won't lead to 0. They would either lead to a number less than 0, or they will never lead to 0 at all. So now that we have created the tree and we have understood what we want to do, let's just also put in one more constraint. Let's say the constraint was you need to return unique combination. So unique combinations would mean I cannot have 3, 2, 2 here because 2, 2, 3 has already been added. Now a unique combination would mean the two combinations are considered unique amongst themselves when at least the frequency of every single number used is different. So 233 and 223 will be considered unique, but 223, 322 will not be considered unique, but because the frequency of those numbers are exactly the same, although the ordering is different. So they are still considered same, right? And so we cannot add this in our output. So now that we cannot add it, let's go back to our state space tree and try to understand how this could occur. We used one of these paths. We said 7, we have 4 options to delete from, and then we have 4 options again to subtract from at first level when we have node 5. But did we ever try to understand that when we are at 3, let's say when we are at 2 here, we have got options from the very beginning to the end. So one trick here to make sure that we do not include same combination twice is to make sure that we use the next integer that we want to delete from the current node based on one condition. And the condition should be that the index of the node, the index of the integer used should be greater than the previous index. Simply put, if you have 7, 2, 3, 6, 7 and you're trying to enumerate all possibilities for this node 4, since you have already looked at 2 before and this is the path that was originated by 3 and index of 3 in the array is 1, you only need to look at the possibilities starting at 3. So you can either delete 3, right? You can either delete 3, or let's assume all of this is far away. Let's just assume that you had 3 here and you had 4. So at 4, because 3, this path that you're looking at was originated by 3 and 3's index is 1, you only have 3, 6, and 7 from your given array to be considered. So you can either consider 3, or you can consider deleting 6, or you can consider deleting 7. Now this way you noticed that we'll never go back to 2 for any path that is originated at 3. Because think about it, if you use 2, you would end up using 3, 2, and 2 again to get to 0, and that would again lead us back to this problem where we have duplicate combinations. And so all we say logically is, let's just avoid all the previous integers that were in the array by just looking at the index. So if we have a path that was originated by 3 and 3's index is 1, we only need to look at integers going forward. So very simple logic is we go from left to right and don't go back. And so let's just, now that we have understood our constraint and the state space tree, let's just quickly code it out. Let's just say we have combinations function, and that function basically takes in the integers as a list and then the target. All right, now let's just also code in our nifty little DFS function that we have been doing so far in the previous videos. And that function should take in a start index and then a current list. Now this current list will be used to store the current combination list. Now let's just establish our exit condition, and that would be if, oh, I forgot, we also need target, right? So we'd say if target has somehow reached 0, then it's time to save our result. So we just create a global variable in terms of the scope of this DFS function, and this global variable can just be an empty list because we need to return a list of list. And then now when it's time to store the result, we just say result dot push a copy of current. So I'm going to use the spread operator here in JavaScript to copy current. Now that I've done that, I just need to end this recursive call. I want to make sure I don't go any further. All right, now that we have saved our solution, let's just also consider one other exit condition to make sure we don't overflow or we don't have the call stack exceeded exception, and that is if target is less than 0 at any point, we just need to end the recursive call. All right, now that we have established the exit or the base conditions, we just need to loop through our possibilities. So I'm going to say for let I equals start. Notice that I initialize my iterator variable to start, and then I say I is less than integers dot length. I want to look at all the integers starting at the start index to the very end, I plus plus. And inside each iteration, I want to first get the num, say integers I. This would give me the num. Now the very interesting thing that I want to check is say, okay, let's push current. Let's push the I into the current. Current is a list that holds the current combination. And let's just call DFS to see if we have reached target 0. And to do that, we just call DFS, pass in the start index as I, because we get going forward in the next iteration, we can start at I and above. And then the current needs to be current. We just pass it along. And then now the target has reduced because we have used this num. So our new target will be target minus num, right? Based on our state space tree. If we go back, we started at 7, the very first iteration. We're going to say, okay, subtract 2 plus 7. Now my new target is 5. So in this case, I'm passing in my new target 5. And then once I'm done testing that path, I can just remove my current num, and it has to be num, not I. All right, now that I have done that, this is a very simple vanilla backtracking template that we have been doing so far in the previous videos, and it should be very simple to follow by now. If you have not watched my previous videos, I would recommend go and watch them now and come back to this question. All right, now that we have done this, all we need to do in our main function is to call DFS. Now start has to start from the beginning, so 0. Current can be an empty list that the DFS function will take care of, and then the target needs to be the original target that is in passed to us, and then we'll let the DFS function populate the result array, and then we just return the result array. Let's just quickly call it to see if it actually works. All right, we say DFS, not DFS, it's combinations, right? So it has to be combinations. And then integers needs to be an array. Let's say 2, 3, 6, 7 from our example, and then the target needs to be 7. It's 2, 3, 6, 7, and the target is 7. Let's try to run it on our online nifty JavaScript compiler and see what errors we get. All right, we did not get any errors. This is the first time pass. We got 2, 2, 3, and 7. As we expected. Now let's look at the space. Let's look at the space and time complexity here. Now let's first address the time complexity. Looking at the code, we know that every time we go through these numbers, we can either use them or not use them. So we have two choices. And so at max, we are looking at a time complexity of 2 to the power n, where n is the length of your integer list, right? And so the space complexity here again is going to be 2 to the power n, because that is the maximum depth of our call stack. And so that will be the maximum number of calls, recursive calls, that we will ever do or we will ever spawn. All right, now that we have looked at this question, I think it'll be helpful for us to use the same intuition to solve similar combination related problems. We have also so far looked at different permutation related problems in the backtracking pattern, and I hope by now you have already gained some confidence and you'll be able to solve similar problems. In the next videos, in the upcoming weeks, you'll be looking at different patterns, better patterns that will help you nail any coding interview in JavaScript. Until then, happy coding. Bye bye.